So it is my pleasure to introduce today's speaker, Marcel Nutz from Columbia University. I guess Marcel is extremely well known to everybody in our community, but let me go through his CV very quickly with you. After receiving his PhD at ETH Zurich about 10 years ago, he moved to Columbia, and he's been there ever since. And now currently he's at the Department of Statistics. And Marcel has his work, we all know. He has done a lot of work on robust finance and other aspects of mathematical finance. And these studies were recognized by the community, giving him the Medal of ETH in 2007. I see it over there, which is an important thing in ETH at least. And he was a Minerva Foundation Fellow at Columbia. And about 4 years ago, he received the Sloan Fellowship. So today he's going to talk about entropic optimal transport, the topic that he's been one of the leaders for several years now. So we look forward to hearing your talk, Marcel.
Thank you much, Mete, for a kind introduction. Thanks everyone for joining this talk. So today I'll be speaking on optimal transport and its entropic regularization. It's not exactly a math finance talk as you see, but actually you see the objects that appear there they look very familiar to math finance people. So I'm actually hoping to get many of you interested in this area, which has really been flourishing recently. So before I get to the entropic part, I'm just going to review the standard optimal transport problem. Everything I say is joint work with at least one of these. Espen Bernton is a postdoc at Columbia. Promit is a postdoc at MIT. He was a student at Columbia until recently. And Johannes Wiesel is a postdoc at Columbia as well. Okay, so optimal transport, let me start with Monge's old problem from 300 years ago. So just to fix my notation mostly. So there are always going to be two probability spaces. Those will be my marginal spaces, x mu and y nu. They're always polished spaces, and I always have a cost function c. So it's a function of x and y. It's non-negative and it's continuous. Okay, Monge's problem is you have a pile of sand here. You don't like your pile of sand. You want to transform it into a different shape at a different location. That's u nu. And what Monge looks for is a map from x to y, which transforms the original pile into the new pile. And we want to minimize the cost. What is the transport cost? We have to bring each sand corn from x to the location t of x. For that, we have a cost c. And then we sum up the cost over the sand pile. That's our total transport cost for t. And then we minimize that over the transport map. That's the original problem. Then in the modern formulation, and especially in probability, this Kontorovich relaxation is very important, and by now maybe the primary formulation. So here we don't look for a map, we look for a probability pi on the product space. Okay, it has the given marginals. In other words, it's a coupling. The set of couplings is called capital pi. And now we minimize the cost in the sense that we just integrate c with respect to pi. Okay, so in this problem, the functional here is linear with respect to pi. We're minimizing over a closed convex set, so there will actually be a solution immediately as soon as this problem here is finite. So script c will be the value function for the given two marginals. Pi star is generally going to be a solution of this problem, and this is truly a relaxation of the Monge problem. Indeed, Monge transports are exactly the ones whose stochastic kernel in this decomposition here happens to be deterministic. Okay, so previously the marginals were seen as fixed. It's also fruitful to see them as variables. Indeed, this total transport cost is a way to measure a distance or discrepancy between the two probability measures, at least for suitable functions c. So if x and y are the same space, we can use this construction to define a metric. Usually it's called Wasserstein or earth movers distance. And two examples are the Wasserstein 1 distance, where for the cost, we just take the distance, for instance, on RD. This is the original Monge cost. The most important situation nowadays for applications by far is W2. W2 means you take the square distance as your cost, and then, okay, you have to take the root at the end for this to have the good properties for a metric. The benefit of this construction is that you can start with any metric on your underlying space and lift it to the space of distributions. That's really the appeal of this whole thing. And afterwards, you can compare arbitrary two distributions, essentially, including, for instance, an empirical discrete distribution with a continuous theoretical counterpart, in a way which somehow relates to your underlying space that you started with. Okay, because you have a metric, there's a geometry coming with it, you can talk about geodesics and so on. In practice, I think, you can say this is a natural way, but somehow to convince yourself, you need to look at some pictures. These are just some random examples. There are many more from applications nowadays. If you do this construction, for instance, here the two marginals are one Gaussian and then another Gaussian, different mean and variance. We interpolate using W2, so basically follow the straight line in that geometry. Then you see that the intermediate points along the lines are again Gaussians, different mean and variance, but they kind of interpolate smoothly in an intuitive way. This is the same thing down here. Here, by contrast, it's the Euclidean way of interpolating where you take convex combination in RD. So here, of course, instead of moving one sort of point to the other where the thing is concentrated, you just blur over, and in the middle you would have two sort of blurry dots instead of a moving point. And it's the same thing here. We transport this to these two disjoint uniforms. It really splits apart in a natural looking way, also in the empirical case. Here, I'm not sure how well you can see it. These faces kind of look reasonably like real faces. They're not just a blurred face in the middle. So somehow that's just to illustrate that in examples, this notion of distance actually tends to make sense. I think that's truly the appeal. Okay, and that's why nowadays we have very, very, very numerous applications in a lot of applied sciences, especially data-intense sciences. This is only possible because in the last few years, people have developed approximate solvers, which really can compute this stuff fast. Okay, so for high dimensional applications, the exact computation of optimal transport is usually too expensive. So the best you can do, so the assignment problem is you have end-to-end atoms, everyone has the same weight. This is kind of the simplest form of the problem. The best you can do is n to the 3. Whereas if you go to an approximate solver for general optimal transport, you can have a delta accurate approximation of the cost in something like n square over delta steps. So this means up to log terms. This is the way it's stated here as a result of my former neighbor, Jose Blanchet and co-authors. And one way how you can get to that result, according to their paper, is you first solve a regularized version of the optimal transport problem for sufficiently small, suitably chosen regularization parameter, and then you actually use that to get your result. So I'm going to be talking about this entropic regularization, mostly from the point of view of approximating the original optimal transport problem, although that's not really the only interest. Okay, so what's entropic optimal transport? Entropic optimal transport means I fix my regularization parameter, a constant epsilon, positive, and then we can write down the entropic OT problem, or EOT. It has the same OT cost as before. This is this integral. It's the same couplings as before, but now there is a penalty, epsilon times the relative entropy between the coupling pi and some reference that I have to introduce. And the reference chosen usually here in applications is the product. So P is P as a product, not as in probability. It's just the product of the two marginal measures. Okay, H is the usual relative entropy, or KL divergence. It's just integrate the log density by the coupling. If you come from math finance, this looks exactly like the dual of exponential utility maximization. C would be that you're also holding a claim or a random endowment. In that context here, you would have martingale measures. Martingale measures are somehow calibrated to increments of a martingale. Here, you are calibrated to the marginals, you can think that you're calibrated to options written on the marginals. Formally, it's the same type of problem. So you will see the same structures, similar Lagrange multipliers. Okay, so just taking it as it's written, this is kind of a trade-off between the first term and the second term. When epsilon is large, we make this term important and this one relatively unimportant, and vice versa. So when epsilon is large, we expect to see something close to minimizer of this. The minimizer of this is actually just P, because P is a coupling, its relative entropy to itself is 0. So it will start to look like a product measure, whereas if epsilon is small, this becomes unimportant, and things should start to look like a solution of the optimal transport problem. So in this vague sense, it's an interpolation between the product measure and an optimal transport parameterized by epsilon. So we can think this is like a vanishing viscosity. As epsilon goes to 0, we hope to converge to an optimal transport. You can see this here in some nice pictures, also stolen from the book of Perret and Couturi. Here, epsilon is large. The marginals are this red one-dimensional distribution with 2 humps, and the other marginal is the blue guy here. So this looks, I think it's better to look here maybe, this looks pretty much like a product measure to me. Then epsilon to the right, epsilon shrinks. This hill here becomes more singular, but maybe again, it's clearer here. You can see this starts to converge to a line, and the limit would indeed be the graph of the optimal transport, which here is just the usual Höfting-Frechet coupling given by a function from x to y. Okay, and you can see that things start to concentrate close to the graph. That will actually be the main theme for much of the talk, how things kind of concentrate towards that line. Okay, some properties of EOT. There are many, many, many. I'm just going to quote a few. So one thing is, just like for exponential utility, you can get rid of the claim by changing the measure. It's a very well-known trick. Okay, here it has a different name. What you do is you convert this to a pure entropy minimization, no, C term anymore, by artificially introducing a reference measure R. R has this Gibbs kernel form relative to the P measure. It's the same thing what you would do with a random endowment in math finance. Okay, and then it's just argmin over coupling. This has a name in the literature. It's the static Schrödinger bridge problem. So it's just Schrödinger bridge projected to the marginals, and it's very well studied. Indeed, it goes back to Schrödinger, at least, if you don't take too precisely the formalization. Okay, also here we see immediately this is a strictly convex problem. We know a lot about entropy minimization in math finance. You're minimizing entropy over a closed convex set. That means basically you'll have a unique solution immediately as soon as the problem is finite. So that solution, I'm going to call it pi epsilon throughout the talk. So pi epsilon is basically the EOT optimizer as soon as the problem makes sense. From the computational point of view, EOT is much, 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 much easier than OT. Okay, in particular for high dimensional problems, the Synchron algorithm is, I think, by far the method of choice. It's very easy to implement. You just have matrix vector multiplication. For that reason, it's very easy to parallelize in GPUs. And apart from this, there are also many other aspects, I think, of EOT that make it attractive in terms of robustness and so on and so forth. It's smooth, so it gives you gradients that you can use in many applications. So there are many benefits. Actually, their book has listed a few. In this talk, I'm mostly interested in solving EOT for small epsilon to approximate the optimal transport problem. Okay, so then naturally you're interested in the quality of that approximation and the convergence as epsilon goes to 0. Okay, so later I'm going to hopefully convince you that the convergence of pi epsilon to an optimal transport pi star happens already under weak conditions. So we're mainly interested in how good this approximation is. In other words, how fast the convergence is. In terms of setting, I'm interested mostly in continuous and semi-discrete optimal transport. Continuous would mean that both marginals are continuous. Semi-discrete means that one marginal is continuous, the other marginal is discrete. Okay, and otherwise fairly general setup. The fully discrete case, our results are not going to be interesting in that case. On the other hand, that doesn't maybe matter that much because there are very good existing results. So
Marcel,
when you have, yep.
There is a question on the chat. So Ibrahim Ekran is asking, what is the relation of this Schrödinger bridge problem to the Schrödinger problem where the final distribution of the Brownian motion is fixed? It is in the chat if you want to see it.
Yeah, that could be a longer answer. So essentially, this is the discrete version, which only the static version that only sees the marginals. If you want to solve that Schrödinger problem, basically you would solve this problem first between the two marginals, and then if the Brownian and you have the square distance, the usual setting, then you have to make a Brownian bridge. So this static coupling tells you, go from x to y, which x to which y, and with what probability. Then you connect the x and y with a Brownian bridge, and that will give you the solution of the dynamic Schrödinger problem in the simplest case. That was a very brief answer probably of the question. Okay. Okay, so if we are interested, if we start with the discrete marginals, fully discrete, really just finitely many points in the support, then optimal transport is just a finite dimensional linear program. So in that literature, entropic regularization has been studied and can be studied in great detail. In particular, if you take the solution of the entropic regularization and any optimizer, you can see the total variation distance going to 0 exponentially. Okay, the way the result is stated here, this is due to John Niles Sweet, relatively recent. It's a beautiful result because you know exactly what the constants are. They are very interpretable. I'm not going to detail it here, but it's really intuitive what's going on. And this is not just a rate, this is actually non-asymptotic. For sufficiently small epsilon with a known threshold, this is just an inequality, that's true. In the continuous case, things are a little different. Let's see the simplest possible, the nicest possible example. Here we have Gaussian marginals on the real line. If you wish, you can take both Gaussians to be the exact same Gaussian. Cost is quadratic. Then you can solve explicitly all the problems. The epsilon EOT problem will have a Gaussian coupling as its solution. In the limit, you will find the Monge transport here, which is just a dilation. Or if the variances are the same, that's actually the identity map. Then this is a meaningful way of quantifying the convergence. You look at, take your pi epsilon approximation. How good does it approximate the solution in terms of how much worse is the transport cost? And then with the quadratic cost, you can just compute this and you will see that it's epsilon plus higher order terms. So you have only linear convergence, nothing exponential. In the example, you have explicit solution. You can understand exactly where that epsilon comes from. And basically, it comes from the mass that is somewhat close to the graph, but not quite there. Then you sum it up all the way, well, it still gives you an epsilon contribution. In the pictures that we saw before, this is all the, the color that's close to the graph, but not quite there. Okay, so this kind of expansion has been studied in some detail, also for other marginals when you don't have explicit solutions. There are two recent references here, Conforti, Tamanini, and Paul. Shomik Paul's paper is closer to ours because it looks at the static problem. So they look at higher order terms. That means you have to go quite fine into the structure. Here, we're going to have a slightly different point of view. Rather than getting stuck here on this linear convergence, we want to focus on the local picture where we don't have to integrate over the whole space. From that point of view, maybe this problem looks encouraging because by writing down the density of the explicit solution, okay, it's Gaussian, you can see the form. And indeed, you see that there is an exponential decay to 0 away from the graph. That's going to be the big thing. So it looks like e to the minus alpha. Alpha is just something like the fraction of the variances, a known constant. And then here you have the square distance to the graph. So you're on the graph if y equal t of x, otherwise you're away. And then you go to 0 as epsilon goes to 0. This is like e to the minus infinity. Okay, so exponential decay, that's something we like to see. And basically what we try to provide is a similar result in the general setting where, of course, it's not like we have an explicit solution for pi epsilon. Okay, we try to say somehow, is there such a decay and what's the rate? What would be the rate up here?
Marcel, there is one more question if you want to take it.
Yes.
And this is in the Q&A, and I don't know who's asking. What is the dependence on dimension of the measures for these convergence rates? I think this constants that we see something like alpha.
Oh, for that discrete result, presumably. So the discrete result doesn't have the dimension in it. However, it has the number of points in the support in it. In some sense, if you're sampling, those would probably be related. And indeed, everything will deteriorate as n goes to infinity. In some sense, the fact that the continuum looks different can be seen that way. Yes, if this is really, you have a fixed number n of points, don't try to push n to infinity at the same time, otherwise it will collapse. But at least it's transparent there. You can see why exactly it collapses. It's really about somehow you have the best optimal transport and you have something like a second best, or you have a phase of transports of equal cost, which is the second best phase on the transport polytope. And it's about the distance between the best and the second best. Obviously, as we move towards the continuum, the separation would vanish, and that's exactly what destroys the convergence rate.
Thank you.
Again, sorry, that was probably a brief explanation. Okay, so what are we shooting for? We try to see the mass of a small ball and how it decays away from the graph. That's exactly the form of this result here. So this is all in the primal side. It takes the shape of a large deviations principle, but you don't necessarily have to think of it that way. Okay, so here I take as given that the pi epsilons converge to some pi. Gamma will be the support of the limit. Then I will be the rate function. I'm going to define it later. We'll discuss how to define the rate function by a formula. And then the statement has the usual lower and upper bound. The first one basically says, okay, the mass of a compact set will decay at least as fast as e to the minus this guy here over epsilon. And the lower part says the mass should decay at most as fast as e to the minus this guy over epsilon. So you have matching bounds, and you really want to think of this. That's the key result, is not just to have this general sets, but think of it, you have a small ball around the xy, then I of xy approximately is the exponential rate at which things go to 0, assuming that xy is away from gamma, the support of the limit. The part A, the lower bound, so convergence is at least as fast, is extremely general. There are no conditions, and there really aren't any conditions. In B, there are conditions. We discussed 2 assumptions, alternative assumptions in the paper. They are still usually considered weak in optimal transport theory, but they don't include all cases, and especially they don't include the fully discrete case. Okay, what are they? Very briefly. Assumption A says that the transport problem has a unique Counter-Rowitch potential. That means that there's a unique solution in the dual problem. In practice, more or less, this holds as soon as at least one of the marginal supports is connected and the cost is differentiable. So it excludes fully discrete problems, and it excludes having the absolute value function as a cost. Then you definitely do not have uniqueness. So that's a different world. Assumption B is maybe technically related, but it's a separate approach. There we just assume that there is a transport map for the pi star, and we impose directly continuity conditions on the transport map. I'm not going to say much about that in this talk. So later in the talk, I'm going to focus mostly on the method, how we arrive at this type of result. Before I get there, let me connect this to the dual. First, if you do the primal, you probably want to know what the dual is if you have any experience in convex analysis. And second, well, I said this is basically saying that the mass of a small ball has this rate of convergence. Then maybe you think, does it mean that the density has that rate of convergence? That would obviously be a very similar result. And that's actually exactly the dual result. So here's the precise form of the dual result with Johannes. So actually, technically, this result is obtained in a completely different way, but the message is very similar. Okay, so here there is an integrability assumption. It's not an unreasonable one to have product integrability for the cost. Here again, I'm assuming that there is a unique dual solution in the OT problem. Okay, and now what are F epsilon, G epsilon? This is the solution of the dual problem for given epsilon. Instead of writing the whole dual problem, which you may recognize, actually the dual problem is just exponential utility maximization. So the solution is the optimal portfolio of that maximization problem. One way to encode it, as you may know, is you take the optimal density and then it has a specific form and the optimal portfolio will show up in the exponent, okay? So that's just a way to say what the dual solution is. You'll have exponential 1 over epsilon, which is like absolute risk aversion in the math finance literature. And then here comes your portfolio, a function of X and a function of Y. These are the options. And then here you have actually the random endowment or claim that you're also holding at the same time. It's like exponential indifference pricing. Okay, so you have these guys. These two functions is what we're zooming into. And the result says that those converge to the dual solution of the optimal transport problem. Actually, this is kind of like exponential utility, take risk aversion to infinity. You expect your portfolio to converge to a super hedging or sub hedging portfolio. Don't ask me, the good inequality. And that's basically what's being stated here in this setting. Let me not say much more about this result in itself, but just see how it connects to the primal one. So this is the formula I had just written. This is the density. This is the form of the density. And what we just said is that this guy here, the square bracket, converges to this square bracket with the star guys, the limiting potentials. Now, under the assumption that these potentials are unique, actually the square bracket here is just minus I, the function that we will define later. There's an explicit or sort of a closed representation in this case. So the dual limit says that the density behaves like e to the minus I over epsilon, which is exactly saying that I is really the convergence rate for the density. Okay, this formula or this difference between the cost and the dual solution, somehow how the dual detaches from the cost, is an object that comes up in optimal transport. So it has been studied to some extent and there is awareness of its relevance. Because we know a lot about optimal transport, this gives us one tool to show that I is positive outside the support. Okay, so before I said I is the rate, but actually if the rate is 0, that doesn't really tell you very much. So you would be interested in seeing that it's positive, at least in certain regions. Maybe I won't say too much about positivity and just refer to the paper for that. Okay, instead, what I want to highlight actually in this talk is the method, which I think is the main novelty of this talk. And it's also, in some sense, a very simple method. I believe it's much simpler than much that has been done before, and it may be flexible for other results as well. Before I get there, let's recall a little bit of optimal transport theory that is probably, hopefully familiar to many. So in optimal transport theory, there is a notion of C-cyclical monotonicity, which basically captures the geometry of optimality with respect to that cost function. It has really become a cornerstone of the theory. So it's the standard way of proving stability results, of proving that a control-weight solution is actually a Monge solution, and so on and so forth. So the basic result is that a coupling is optimal if and only its support is a cyclically monotone set. What does it mean to be a cyclically monotone set? So a set here, this is a subset of the product space. It's cyclically monotone if it has the following property. You pick pairs from the set, finitely many, an arbitrary number, and then you compute the discrete transport cost. Okay, here you're transporting xi to yi, compute the cost just for those, like in an assignment problem with no weights, just sum it up straightforward, and compare. Compare with what? Take the same pairs, but now permute the destinations. So look at alternative discrete transports between those points. If this inequality holds, it means that changing destinations does not improve the transport cost. Somehow that means the original set is already good in terms of transport. It doesn't have detours if you wish. Okay, so that's cyclically monotone. And then this result holds as it's stated up here. Okay, usually the notation is a little different. This is usually written as I+1 because you can always choose the indices the way you want it, so that becomes equivalent. Okay, now this is a very important and to me very nice part of optimal transport theory. And as far as I can tell, it doesn't have a counterpart in the EOT literature. So we want to do something in this spirit. The counterpart cannot be completely direct for an obvious reason, namely in EOT, all relevant couplings have the same support as the product measure. So the support is actually not informative. We'll have to write a condition on the density instead of just the shape of the support. Okay, but apart from that, maybe we can still have something in a similar spirit. Okay, so here's a definition. We baptize a coupling to be cyclically invariant instead of monotone, because there will be an equality instead of an inequality, if it's equivalent to the product measure and its density has a specific property. Okay, it's written down here. What you do is, as before, you take pairs, k many of them, then you take the product of the density along the pairs, and you hope that this has a specific relation with the similar product where the destinations have been permuted. Namely, I want to have the equality with this strange term here. It may not look exactly as before, but in a way, in OT, if you know the theory, C-cyclical monotonicity expresses the form, the algebraic form of the dual solution, and this does exactly the same. Another way, namely, of stating is that, okay, I could make this formula look prettier. I could write here this reference measure R with the Gibbs kernel that I introduced before, and then just delete this term. That's the same expression, just rewritten. Okay, so then you recognize the product structure, and in fact, this is just another way of saying that that this density is a product of a function of x and a function of y when you take it relative to R. Okay, so it really expresses the algebra. However, today I like the ugly form more for once. Why? Because I'm interested in epsilon to 0. Actually, this is looking great. The expression here is exactly the comparison that comes up in the C-cyclical monotonicity definition. The epsilon is exactly here and nowhere else. It's really explicit. So if you want to analyze the limit, this seems to be a very good formula. Indeed, the first thing you see is that, okay, somehow I want decay of this density. If this square bracket is positive and epsilon goes to 0, this starts to look like e to the minus infinity. That's exactly what I want. Okay, it's maybe a bit strange because I'm in the k-fold product, but never mind. Somehow this gives me good hope. Okay, somehow I'm going to be just playing with this, integrating it over specific sets and hopefully getting a result from that. Okay, so we made a definition. What's the relation with optimality? Firstly, if the EOT problem is finite, the relationship is absolutely straightforward. You have only one cyclically invariant coupling, and it's exactly the minimizer. You could look at the problem even if it's not finite, be more ambitious. Then what's always true is definitely uniqueness. That's easy. What's less obvious then is existence. Here you have existence from the optimizer. So in the finite case, it's clear. It turns out that at least on Euclidean spaces and other finite dimensional spaces, we can prove existence in completely different way. And then, so maybe it's just always true. It's definitely true in a very large class of spaces that existence and uniqueness hold. This more exotic consideration is analogous to optimal transport. The message here is that actually what I wrote before is not just a reformulation of the dual solution, but rather this geometry has a meaning on its own. And that meaning persists even when the optimization problem just doesn't make sense anymore, because if every coupling has infinite cost, the optimization doesn't really make that much sense. But the geometry still makes sense. So in optimal transport, this is known. And for instance, you can define Bernier's map even if the marginals are not square integrable. This has been used. And in a way, this is just an analog of that you can always use the geometry even if the value functions don't make sense. Okay, so now some ideas, mostly to give you the spirit of how to work with this definition. Okay, well, plainly speaking, you have to integrate over sets because you're working with a density. This is a very simple result that expresses what I said before, but it's actually crucial. Okay, what am I saying here? Let's define a delta improvable K tuple. Sounds horrible, but what I mean is it's a pair, K pairs xi, yi, so that when I look at the transport cost, I can improve by changing destinations by at least delta. Okay, so these are actually bad K tuples. Okay, this is the expression from the square bracket over here, what I said. Now I'm just assuming that I'm basically looking at the set where this is bigger than delta. So there, this 1 over epsilon is going to draw everything to minus infinity. That's exactly what this result does. Namely, with this delta, the k-fold product measure of pi epsilon of this whole set, and of course every subset of it, has to decay exponentially with rate at least delta. There is also a converse bound, so you may be interested in such a result as well. That one is only asymptotic, okay? It's only as epsilon goes to 0, not for all epsilon. It's a little more delicate. So that corresponds to having an extra delta, on the other side. Let me not detail. I'll just explain the easiest things to give the intuition. Okay, so before I tell you how to go from here and this strange k-fold product to the original theorem, let me give you another application which is actually significant to clean up something I said before will be true, but now we can actually give a proof. So what are we trying to say? We're trying to say that as epsilon goes to 0, suppose you have a limit point, a cluster point, call it pi. Then that pi, I said, is an optimal transport, and the more general way of saying it is to say that its support is C-cyclically monotone. The proof of this is a 2-line argument, and it's basically the same argument that one is used to in optimal transport. You ask yourself, maybe it's not C-cyclically monotone, then I find a k-tuple that's improvable by some number delta, and then you basically contradict it just using this result here, because this says your measure goes to 0, but then measure going to 0 and being in the support are not compatible. Done. That's a rigorous proof. I kind of claim that this is much easier than gamma convergence arguments that are known in the literature and which could get somewhat tricky, especially when you want to carry them out in a general space and for a general cost. In addition, this result doesn't talk about the value function, so it's always true. Okay, it just uses the geometry. Gamma convergence is a technique which starts with the convergence of the value function, and presumably it doesn't tell you anything if the value function is just infinity. Okay, so where does the cluster point come from? Existence of cluster points is trivial because the set of couplings is weakly compact. Okay, take a sequence in there, it will always have limit points. The only question is, do all these cluster points agree with one another or not? But given this result, if we know that the optimal transport problem has a unique solution, or more generally, a unique cyclically monotone coupling, then, well, this just says that all cluster points are equal to this one guy pi star. Therefore, we have convergence proved. And this is the most relevant setup, definitely for applications. If one marginal is continuous, usually we have uniqueness of transports. And in most cases, it's actually given by a transport map. Okay, there are some other cases where the convergence is known. I don't think it's known in full generality. What you expect is that somehow pi epsilon has minimal entropy, so the limits should have this property as well. If there exists an optimal transport with finite entropy, then there is also one with minimal entropy, and then that guy will naturally be the limit. That's not hard to prove. Okay, just that in the continuous setup, very often all optimal transports have infinite relative entropy, and then this doesn't really give you anything. The other example where convergence is known, as far as I know, is the one-dimensional Monge problem, so distance cost. That's this paper by Di Marino and Louet. Otherwise, in general, I'm not sure there are results. But I would certainly conjecture that convergence is somehow always true. All right, with that, let me get back to how to use this result to get back to the large deviations type statement. So what we need to do, so this is a bit strange, we need to get rid of this k-fold product that's in some space which is not in our original problem. Okay, as I said, we're trying to get the measure of a ball around x, y to decay. Now, so the ball has a center, that's my point x, y. Now, how am I going to connect this with the lemma? The way we'll do it is we take the point, we nickname that point x1, y1, and then we're going to keep adding other points that we invent, I equals 2 to k, to get a k-tuple. Now, let's hope we can find a k-tuple where we have this delta improvable cost. Okay, then by applying the lemma, I can get to the statement here or something similar. The lemma will give me a product of k factors decaying exponentially. Now I need to ensure that really the first factor is the one that has the decay rate and that the other guys don't interfere. And the way to ensure it is that these other guys are in the support. Because they're in the support, their mass will not go to 0 and they won't interfere with the exponential rate. That's the idea. Okay, so now that you have this result, for any such k-tuple, you get this delta basically up to a small shrinkage. So now it's very natural that you say, okay, let me optimize over delta. So let's choose good k-tuples to improve the delta. And that's at least a bound for the rate. Okay, so that's the definition down here. I'm gonna optimize over all the k-tuples starting with the relevant point and look at the deltas that I would get from those. Okay, that will be a lower bound for the convergence rate. Essentially, we have gone through the proof, even though I went very fast. What is not obvious at this stage is that actually this is sharp. And that's basically the upper bound. I'm not gonna say much about the upper bound. Just let me quickly check, are there questions in the chat right now, which I don't really see? Okay, if not, then I'm gonna add one more statement, which is in a slightly different direction, but uses the exact same methodology. So it may make sense to put it here. It's the question of stability, which also I haven't seen answered in generality, at least before. Okay, so now it's again about limits. Cyclical monotonicity is very good to deal with limits. Here, the limit is completely different from before, but the method, as I said, is similar. Namely, the epsilon is fixed. You can take it to be 1. Okay, we're not pushing the epsilon anywhere. Instead, we are varying the marginals. So we have a sequence of marginals, mu n, nu n. We assume they converge weakly to some limit mu nu. What you would hope or expect is that if you have solutions of the EOT problem, and you call them pi epsilon n and pi epsilon star, say, for the limiting couple, that those solutions should converge. In optimal transport, the analog is a well-known result. One needs to be a little bit more careful because there usually one doesn't have uniqueness of solutions. So there the statement would be that every cluster point is an optimal transport. But here, since we have uniqueness, all those cluster points would automatically agree, and we expect to just see the convergence. The way this is proved in optimal transport is using this geometric method. It's really just a 5-line proof. You take the limit, you look at its support, you take a k-tuple, you ask yourself, is it cyclically monotone? That's all you need to prove. And then basically by looking at the pre-limit and the convergence, well, you see that if it's not cyclically monotone, you get a contradiction to the pre-limit being cyclically monotone. This works very naturally because you have supports and you have a weak convergence. So basically you just use the Portmanteau theorem. Okay, that's why it's a 5-line proof. But we want to still use the same general idea to resort to the geometry. And so here's the general theorem we have. You take a sequence of cyclically invariant couplings with respect to their marginals. Okay, take the marginals to converge to some limit, mu nu. Then these guys will actually converge to some limit, and that limit is cyclically invariant. So if the value functions are finite, this is saying that the optimizers converge to the optimizers. If the value function is infinite, the theorem still holds as is stated. Okay, if in the case of infinite value functions, this is interesting in particular because it gives you an existence result. Okay, basically, if you're only interested in mu nu, you can always approximate mu nu with some very nice marginals. For instance, you can take an empirical sample, okay, take a finite discrete measure converging in the sense of weak convergence. Okay, this is finite dimensional, so you just solve it. You can definitely easily find this coupling. And the theorem tells you that there is a weak limit and that guy is cyclically invariant. So we have just proved that we have a cyclical invariant coupling, even when the optimization problem doesn't immediately make sense. So here the proof is a little bit more delicate than in optimal transport, because as I said, in optimal transport, you have just the support and you have the weak convergence. They go together very naturally. Here you're basically trying to pass to the limit of the density, but the density will not in general converge under weak convergence. Okay, for instance, like I just said, this could be discrete and this guy continues. So it's a little bit difficult to talk about the pointwise convergence of the density, and there will be some, I guess either we need to integrate the density or we need to differentiate the measure. That's going to be a delicate step involved. And that's probably why, at least the way the result is stated here, we prove it in Euclidean space, or more generally, any space where you can differentiate measures in the usual sense. So I'm not sure at the moment if this would still be true in infinite dimensions, although, I mean, I don't see a reason why it wouldn't be true, but I also don't know exactly how to prove it. All right, so I think my time is exactly up. I think this is a very good time to say thank you very much for all your attention. In a relatively technical talk, I hope you can see the relation to math finance and get more interested. There is a lot of interest in this entropic regularization at the moment, as I realized over the last year or so. So thank you.
Thank you, Marcel. Let me clap for on behalf of everybody else. So it's time to take questions. You can either turn yourself on and ask the question or write it in a chat or Q&A. Yeah. As we wait for the others to ask questions, so I have a couple of questions, Marcel, maybe I start. One thing is just a curiosity, the theorem at the beginning, that the convergence theorem that you stated with open sets and closed sets, you remember that one? That looks very much like his statements coming that one sees in large deviations. So is there any...
the form is a large deviations principle.
So is there any connection beyond the formal look of it, or anything deeper than that, or?
Yeah, it is a type of large deviations principle as epsilon goes to 0. So, in the more physics interpretation of the Schrödinger problem, this would be either small time horizon limit or small randomness or small temperature. I think people would say 0 temperature limit. If you're thinking of a standard large deviations principle where you have something like IID random variables and things converge to the average, which is a number, and then you talk about how far are things from that average, then here the analogy is that you have convergence of the pies. Sorry, I need to switch back to this mode. You have convergence of the pies, and okay, here instead of the number, maybe you think of the support of the limit. And the question is, as you go away from the support, how fast is the decay? So just like how fast is the decay away from the average, that's the analog really. Like this rate would be 0 on the support, and away you can hope for exponential decay. That's kind of what it says.
One thing is that, like in the Varadhan's book, I think that's called contraction principle, that if you have this result, then you have convergence result for exponential type of functions and that type of things. I don't know whether that is relevant or useful in this context, but that's what I was a bit...
Yeah, for some things one has to be a little bit careful. Like I guess this in their language, this is maybe called rate function or weak rate function. It's not a good rate function. So here the limit, it depends on what you're interested in. If the marginals are compactly supported, the way in regularity theory of optimal transport, things always assume to be very nice, then basically you can make your whole space compact, and then this compact set is just a closed set and exponential tightness holds and so on and so forth. However, from the apply point of view, actually, we are quite interested in unbounded supports. And then that's not really clear. So because this support will already be a non-compact set necessarily, I guess exponential tightness a priori can never hold. So that's where the discompactness is maybe an easier statement.
So there are the Rene and Daniel want to ask questions. You want to go ahead first, Rene?
Yeah, Marcel, you mentioned Brenier in your talk. I don't remember in which circumstances, but is there an analog of Brenier's theorem in the sense that if one of the measures, for example, is absolutely continuous, you have a very, so here, is there an analog of Brenier's theorem? For your,
in the sense of having a map, or I'm not sure in which sense. I mean,
the transport is given by a gradient of a convex function, something like this.
I mean, they're never transport maps because when epsilon is positive, if pi is given by a map, this entropy here on the screen will be infinite. So that will definitely not be the solution. That we will only see maps as in the limit as epsilon goes to 0. And before that, all maximizers will be equivalent to this product measure. Sorry, all minimizers will be equivalent to this product measure. The best analog would be that, well, the density of the solution can be expressed with this dual potentials. And, you know, I guess you can say something about these potentials and how they're related. Maybe that would be the best analog I can think of.
Okay. All right. Thanks.
Sure. I think Dan was next.
Yeah, hi. Thanks for the fascinating talk. I'm curious about, so you already answered one of my questions, which talking to Mete about this seems to be a weak large deviation principle in the sense that you only have compact sets in your upper bound.
Yes.
But I'm kind of curious what else kind of the standard fare from large deviations theory can give you insights in this problem. For instance, the Gibbs conditioning principle tells you that the optimizers of your rate function on a certain set will tell you kind of qualitatively that that's the most likely way that rare event will happen, but that requires the upper and lower bound to match on that event. Are there kind of any cases where that sort of situation is tractable for you guys, or not so much?
Well, the upper lower bounds match, right? If you look at the,
no, but one's over closure, one's over an interior. This is what I mean by matching.
Yeah, but then, yes, I understand, but okay. So on this side here, you have the pi epsilon, which will be equivalent to the product measure. So if your product measure is nice, you know exactly whether boundaries of balls, say, have 0 mass, and I guess they do in most interesting cases, correct?
Mm-hmm. Okay.
And then here, it's the question, you know, could you have a jump in I? That could be a slightly more delicate question, but in many cases, so for instance, when we have the formula I wrote here, in many cases, we know that the optimal transport potentials, okay, we have a very good understanding of the regularity of these guys. And then here's just C. So immediately you know something on the regularity of I. For instance, if you're in the Lipschitz case with compactly supported marginals and a reasonable cost function, you know that I is actually going to be continuous. And then here, there's no question whether adding the boundary to a ball will make a difference, and they really match.
Okay, so in that case, then you'd have, really that there's a single point that where most of the mass is concentrating in some sense. If you
the minimizer. Mm.
But the I does not have a unique minimizer, but only on certain events it might have a unique minimizer, right?
Okay.
Okay, I'm taking up too much time. I'll accept.
No, that's true. Like it wouldn't be hard to make up examples, I guess. Well, it depends on the cost function, right? This is all in a very general context. When you specialize the cost function, it becomes more projection-like. But yeah, I'll be happy to speak in more detail.
Okay. There is a
Thank you.
Jan Obloy wants to ask a question, and then Julian also afterwards. So go ahead, Jan.
Hi, Marcel. Great talk, thanks. I was thinking, so, throughout you had the measure P, which was the product measure, which is fixed, right? But you could think about having other measures there. So do you think there is any scope to improve the rates of convergence if you were able to design measure P? Or would there be an algorithm where you can keep changing measure P as you go? So you do one iteration and then, you learn the reference measure and then you change your P, and somehow that could improve your speed of convergence?
Yeah, that's actually the first thing that came to my mind when I saw that. So in the applied literature, it seems that they always take the product measure, at least in the machine learning literature. There are several comments. Can the rate be improved by changing the measure? The answer is yes, but I'm not sure it's an interesting fact, okay? Of course, if for P, I take the optimizer from here, pi star, the solution pi epsilon is already equal to pi star in the pre-limit. Done.
Sure, but you don't know
convergence
pi star, right?
is infinitely fast. Yes.
But you don't know pi star, so.
True. But yes, so I guess one convenience is that this one is very easy to work with. If we replace P by a measure which has a similar structure, but it's not mu and nu, it's some equivalent measures to mu and nu maybe, then you can get a sort of closed form relation. That's not a completely different problem. You can just parse how one becomes the other. So that may not be such an interesting improvement. If the measure is not equivalent to the product, then things change quite a bit actually. So especially when you start to shrink the support.
So if you did the obvious thing, so you just took, say, epsilon equals 1/n, and then in the n+1 step, you take P to be the pi star n from previous step. So you keep updating your reference measure using the optimizer for the entropic optimal transport from the previous step. Would that, have you looked at what this gives?
I have not, but I think, well, at least theoretically, you can definitely do this, right? Whether you can easily compute this afterwards is a different question. But that would definitely, I mean, you can see what it does, right? It brings you, the penalty is less severe in the sense of dragging you away from the limit. So you expect faster convergence, yes. Okay, sorry, thanks. I cannot give you a precise result off the top of my head.
Julian has a question, and you want to go ahead, Julian? I don't know whether he heard me, maybe we lost him.
Did he write the question?
No, he did not write the question. He just said on the chat that he wants to ask a question. So while we're waiting for Julian, let me ask one question that I had as well. On the computational side, you say that entropic problems, there are good and efficient computational techniques. And the idea is that I guess you approximate the original problem with a small enough epsilon and then compute the approximating problem. But in the PD literature, that I don't know whether there is an analogy here, but then when you have small parameters, sometimes the numerical methods slow down substantially. There is stiffness coming in and all that. I don't know whether I don't know whether you're aware of the computational approaches to this.
Yeah, there are absolutely difficulties. So computationally, you cannot just push the epsilon to 0. There are several instabilities that will show up. So there are actually limits of how far you can go. Yes, in practice. It's still interesting to understand, to have a theoretical understanding of seeing better what epsilon you really want to choose, where you really want to cut off. But you cannot just do it arbitrarily small in a real world application. That's true. Well, firstly, it will get harder and harder, and the conversions will slow down. So, okay, so in the ML literature, it's often said that entropic optimal transport escapes the curse of dimensionality and blah, blah, blah. But one has to be a little careful that these are statements for fixed epsilon, and all this goes the curse of dimensionality, the true curse of dimensionality is that it's never really gone. It's just hiding around the corner. So if you pushed epsilon to 0, the curse comes back and the computational difficulties explode. So it's a trade-off in practice about choosing the epsilon. I think it's reasonably well understood in terms of approximating the value function. What exactly one can do with using pi epsilon instead of pi star is, I think, only partially understood. Like, how good an approximation of a transport map can you get out of pi epsilon, and how? That's something we're thinking about, but I'm not sure there's that much on it. In the ML literature, there's an interesting development where people say, let's just use the EOT problem for fixed small epsilon and don't even try to pass, do the OT approximation. This problem has a lot of nice properties. And maybe, you just do something similar to Wasserstein, but everything entropic, and then just use this and see what the properties are. And sometimes they turn out to be quite good.
Okay, Julian, you want to go ahead right
yes.
now?
Hi, Marcel, can you hear me?
Absolutely, hi.
Okay, sorry, there was a sound issue when I tried to ask my question. Thank you so much for a fascinating talk. Marcel, I had two questions, actually. The second one is basically the question that was asked by Jan. First one is, so you mentioned, I think in the beginning of your talk, that you're considering cost functions that are non-negative and continuous. So basically my question is if you can consider like a more general cost functions. In particular, it looks like you need to be able to integrate the exponential of minus c over epsilon, when you do the change of measure. Is it the only, do you think that the theory will work as soon as this exponential of minus c over epsilon is integrable with respect to the product
Indeed, you
measure?
have to be a little careful. If you allow negative values, you would have to check carefully if it's unbounded below. If it has a lower bound by a constant, then it doesn't make any difference.
Sure, of course, but it's like
if that one goes wrong, you would have to check some additional things. The continuity is a bit more important. So for instance, this convergence pi epsilon to pi star is definitely wrong if the cost function is only, say, lower semi-continuous instead of continuous.
Okay.
I mean, it can be wrong. It's easy to cook up an example where it's wrong.
And do you think
that's more stringent?
Do you think on the other side, so of course, if C has a lower bound, that's fine. Do you think it's the only thing you need is that this exponential of minus c over epsilon should be integrable with respect to the reference measure that you choose to be the product measure?
Definitely for the basic theory for fixed epsilon, that's absolutely true. Maybe one can escape even that assumption by doing a little better. I never went through the limit type stuff because apparently people only care about non-negative and mostly about quadratic. Of course, if you start to push the epsilon, this assumption becomes a little stringent because as epsilon goes to 0, right, you're asking for more and more exponential moments.
Yeah, exactly. So it could be, it's quite demanding.
So it's not far
actually
from asking for a lower bound.
Exactly. So it's very demanding. Okay, so second question was really about exactly how would the result change when you change the reference measure? So basically that was the question asked by Jan, who had more precise version of his question. So do you because actually
I definitely don't know something very precise. So there are
okay.
some trivial results. I'm not sure exactly how many other results there are along the lines of this.
Because in the financial applications that I'm looking at currently in this, basically it's just a pure Schrodinger version. If you want, epsilon is equal to 1, c is equal to 0 if you want. Then the reference measures that I'm considering are, they are not this product measure, or they're not even they don't even need to be absolutely continuous with respect to the product, things like that. So it's, yeah, it could, just to tell you about that.
So for the rate, I definitely haven't thought about it. Especially when it's not absolutely continuous, there are some well-known difficulties in the Schrodinger bridge literature. Then those are a bit more serious difficulties, actually. Yes, I've also looked, I don't know if you have a hedging thing. So I've also looked at the martingale version of this, which I didn't talk about at all. So you have an additional term there. That seems to be quite challenging problem. So by now we know the shape of the density. I would be happy to share those results offline.
Well, not only do you have the martingale, but also including information on the VIX, so it's like also on the dispersion.
Okay, so we have like options and stock.
Exactly.
Oh yeah, let's look at that actually. It's nice to know that you're also interested. Thank you.
Absolutely. Thanks, Marcel.
Thank you, Marcel. I think we don't have any more questions. Let me pause a second if there is anybody who wants to come in and ask. I don't see any. So again, thank you very much for a wonderful talk, Marcel. And I don't know, Igor, we have any plans of continuing this thing afterwards, or
sure. Yes.
Let me hand it over to you.
Yeah. So maybe I'll first of all stop recording. So we